Hello. So it's a pleasure to see you all again. I was going to say good morning, but it's not good morning there. It's good evening, I think. What we're going to do today is we're going to talk about set theory. And you may have seen sets before. I'm sure you probably have. They're extremely important in mathematics. And we're going to talk about sets of numbers, lots of sets of numbers. So it's very important that we review what we did yesterday. So we're going to start by reviewing sets of numbers, but we're going to be thinking of them as sets right now. So let me share my screen. Okay, so yesterday we talked about the different kinds of numbers. And one thing I want to clarify, well, actually, I'm not really going to clarify it, but I'm going to tell you what I think about it. So there's this set of numbers. This is really the first set of numbers we want to think about. And I like to call these the counting numbers. And I like to call them the counting numbers. You know, a lot of people call them counting numbers. But the reason I like to call them counting numbers is because that's how you count. Then there are what a lot of people call the natural numbers. Now, some people like to call these the counting numbers. So if what I'm saying doesn't agree with what you're familiar with, it's because not all the mathematicians agree. Now, to me, you don't start counting with 0. If I ask you how many mangoes you have, you don't say 0. You say, well, I don't have any. If you have 5, you say you have 5, but you don't say you have 0. Of course, if you're counting stuff on a computer, then if there's nothing there, you start counting with 0. So whether you call these counting or natural or something else, it's not important. But everybody agrees on the integers. And these ... mean it goes on forever. So it goes on forever in the negative direction, and it goes on forever in the positive direction. So these are the integers. Oops. And it doesn't matter how many I give. I could give 4 here. I gave 7 here. You have to give enough so that somebody who's looking at what you did knows your pattern. So when I say 1, 2, 3, everybody knows the pattern. And this in books is a bold Z. But what mathematicians do to make it bold, rather than try to make it big and bold on the blackboard, let me do it better so you can see what mathematicians write it like this. They have a double line there. So when you do bold Z, that's the integers, all of the integers, positive, negative, 0. And then the rationals, that's a bold Q, so we put that line in there. And that, okay, now I can't make a list of fractions. You know, I could do 1/2, 1/3, 1/4, but then you think I'm going to do, you know, just those numbers. So this is one place where set theory comes in handy. And you've probably all seen this. So when we draw these curly brackets like this, we mean a set. So these are going to be the rationals. Okay, so these tell us we have a set. And when we give the set like this, it's like a roster. So we say that this is the roster form of a set, like a class roster. We just give a list, one after another. And again, if we want it to go on forever, we have to put ... and we have to give enough information so that anybody else who looks at it can understand the pattern. Okay, so then we have the integers like this and dots in both directions. So this is roster form. Now this, when I give the rationals, I'm going to give what's called set builder notation. So I'm going to build the set up. And the way I'm going to build it up is I'm going to say it's the set of all n over m such that, so this line here, it's called different things in different contexts, but in this context, we say such that. That's how we read it. And we say this is the set of all n over m such that n and m are integers. Okay, I didn't need as much space as I took here. Okay, so that's the set of rationals. And we talked yesterday, there were some important things about the rationals, two very important things. One is if we have a fraction n over m, n and m are integers here, just like they are up here, can be converted to a decimal fraction. Well, it might not always be a fraction, but we can convert it to a decimal, some kind of decimal. Okay. And we do that by long division. And if we have something like 5 over 2, when we convert it, we'll get 2.5. We didn't do a problem like this yesterday, but I know you've seen problems like this way back. And we call this a terminating decimal, because terminate means end or stop. So we do the long division and it terminates. And then I really can't remember what happened when we got 1/7, but I'll just do 1/3 because I do remember that. If we do 1/3, we get 3, 3, 3, 3, 3, like that. And that's a repeating decimal. So if we have a rational number, we know that represented as a decimal, it's going to be either terminating or repeating. And the other thing that we saw yesterday, which is important for our understanding, it's not something you do very often, is if we had a decimal like 0.312, 312, 312, we know that we can convert that to a fraction. And we had a technique for that. We called it X. And it didn't matter that it went on forever, because we can just imagine, okay, this is a number. We know that it's a number somewhere on the number line. And if it doesn't end, that doesn't bother us, because our consciousness, our awareness can encompass all of that. Okay. And then we said, well, if this is a number, we can multiply it. And yesterday, I think I multiplied by 100, but I want it to cancel out. So I'm going to multiply by not 100, I'm going to multiply by 1,000. So 1,000x, that's going to move the decimal over 3 places. That's 312.312 forever. And then let's see, we still have our x, and that's 312 forever. And now I can subtract. So I'm going to do a subtraction. Up, up, up. Ah, my pen got wild here. We're going to just, oops, we're going to subtract. And we're going to get 999 x's. Subtract 0 from 312, and we get 312. And then here, we're going to have a pattern. And yesterday we mentioned that if we want to handle infinity, we can't do it step by step because, you know, we'll just run out of time. So what we do is we have a pattern, a procedure, a technique. Okay, so we have to handle infinity another way than we were used to handling numbers in grade school. Okay, so we say, well, there's a pattern here, and they're going, and that's why we used 1,000 and not 10 and not 100, and not 10,000. So we have a pattern here, and we see these are all going to cancel out. So it's just going to be this, and then we can divide both sides by 999 and get 312 over 999. And then we want to get that in lowest terms. And tomorrow you'll see why I know that this top is divisible by 3. Actually, it's easy to see it's divisible by 3 because 3 goes into 3 and 3 goes into 12. But we'll learn another technique. So divide 3 in there and we get 104. And over here we get 333. And I'm not sure I can do better than that. 4 goes into this. This, yeah, this is the best we can do. So this is this decimal written as a fraction. So we started out with a, but it had to be repeating. We started out with a repeating decimal, and we ended up with a fraction. Okay. And then yesterday, we also talked about the real numbers. And we used a bold letter for that, so that's why we have these 2 lines. So we talked about the real numbers, and they're more complicated to describe. What I said was, well, let's think of a line. Actually, let's go back up and think of the rational numbers, because there's something interesting about the rational numbers too. I can put the rational numbers on a number line. 0, 1, a half. Let's see, a fourth, 3/4, 3 halves would be somewhere out here. So I can put them here. Now, these numbers and along these rationals, they're not like beads on a string. So I just happened to have a necklace on today. I wasn't planning it this way. But if I have beads on a string, each bead has a bead next to it. Okay, there's a bead and then a bead and then a bead. But here, it's not like that. If I took a magnifying glass and I looked between a quarter and a half, well, let's see what we find here. This is a quarter is 2/8, and this is 4/8. So 3/8 is in here somewhere. And then let's see, a quarter is 4/16, and this is 6/16. So I could find something in between here. So these are, and there's even a word in mathematics that's a technical term, but I think it makes sense, even not technically. We say these numbers are dense, okay? Okay. Okay, I'm looking at the question. Okay, so is it clear why I multiplied by 1,000 instead of 100? Because I had to make it cancel out. And okay, I'm getting people repeating as recurring. Yeah, repeating is the same as recurring, but computer scientists use recursion in a very special way, and somebody, okay, somebody is asking an interesting question. They're saying, okay, they're asking me, what about 0.9999? Okay. I want to put that off till a little later, okay? So if I forget, remind me, but I won't forget because for Cantor, it was very, very important actually. So the real numbers are even more dense, if you can imagine that, more dense than the rationals, because the rationals leave holes. For example, the rationals don't have a square root of 2. So somewhere in here is the square root of 2, but that's not rational. And pi, somewhere after 3.14, that's not rational. Now, somebody said, can we round off? Well, in practice, in daily life, we absolutely have to round these numbers off because they're infinite. But in mathematics, we like to be absolutely precise. And when we're absolutely precise, especially with things like square root of 2, we have to deal with them as ideas, as concepts. If I want to talk about 2, I can talk about 2 pens. If I want to talk about pi, it's an abstract idea. But if I want to be absolutely precise, I have to, pi has to be an idea. And you can, of course, compute it to many, many places. You know, if you're designing something, or if you're sending someone to the moon or to Mars, you have to know pi to many, many places, but, or whatever numbers you're dealing with, but not here. So when we talk about the real numbers, we talk about a continuum. The real numbers, the rational numbers had gaps. So up here, when we have rational numbers, we had gaps. The real numbers, there's no gaps. Okay. And we like to think of the space around us as continuous. There's no gaps. We move from here to here. it's not a jerky motion. It's not like we go from here to here to here to here, but there's no gaps. And in fact, mathematics breaks up into two parts: continuous mathematics and discrete mathematics. And continuous mathematics is what physicists, biologists, chemists use. Discrete math is what computer scientists use, because in a computer, there are gaps. You have bits. Okay? So let's see. The complex numbers. And we have the C, and this is a bold C. And if you look on the handout that I sent, you'll see I used bold, but sometimes this is called blackboard bold. It's an attempt on a blackboard, now on a whiteboard, to make it bold. Because otherwise, you want to use C for other things. And R, you want to use R to be a set, so that's different. Okay, so complex numbers. One thing you notice as we go through this sequence, we keep adding on more and more and more numbers. And here we just added on 0, and then we added on negative numbers, and then we added on fractions, and then we added on, to get the real numbers, all the stuff in between the fractions. And now with the complex numbers, we're going to add in one number but more than one number. So this is what we add in. This is the special thing that we add in. But we also are going to add in 2i, 3 plus I, 5 plus 6i, 7 minus I. We're going to add in all multiples and sums of I with the real numbers. So the complex numbers is an extension of the real numbers. And the beautiful thing about the complex numbers, and I said this yesterday, when we look at the Cartesian plane or the plane of analytic geometry, we call it R squared, or R times R. Of course, if this is not a multiplication symbol, it means we're taking pairs. And so we have 1, 4. And this is what you use in analytic geometry, when you're studying straight lines, in calculus, when you study functions. You have a real number here and a real number here. You have pairs of real numbers. And you plot them like that. And you treat them as there's a 1 and there's a 4. Or there's an X and there's a Y. So we call this R squared or whatever. And we'll be talking more about this today, actually. But when we talk about the complex plane, this is the real axis. And this is the imaginary axis. And we might have 1 plus 4i. And over here, 1 and 4, it's exactly the same point. It's in the same place, but it has a different interpretation if we're over here. And this is going to be important for us when we study the Mandelbrot set. So here we have 1 plus 4i. And what's so nice about this? Well, they're both nice, actually. Here, if you have y equals f of x and you want to study y equals f of x, this is where you want to be. And you graph it and you say, oh, it's a parabola, or oh, it has a slope, or it has an intercept. You have all these interesting things over here. But over here, when you graph things, this is one number. It's not a pair of numbers. It's unified into one thing. And we can talk, and in fact, we use a different letter for it. We call these Z, or Z, small z. If you want to talk about a complex number, you use a Z. And so I can say Z squared. That's my Z. I don't know if you're going to have to get used to it. And that would be like for this one, it would be 1 plus 4i squared. And that's going to be, let's see. I'm going to do it out. I know you can do it in your head more quickly, but just for the just to go through it carefully, that's going to be 1 times 4i is 4i. 4i times 1 is 4i. And this is 16 times I. Oh, somebody's got the answer in the chat here. So we're going to have 1 plus 8i. And then I times I is minus 1. That's going to be minus 16. So it's 8. I'm not going to write it that way. The convention is, just so everybody's answers look alike, the convention is to write the real part first, minus 15 plus 8i. I see in the chat some people have 8i minus 15 because they like putting the minus second, but this is the way, this is the conventional way. If you were to write, if I were giving you a test and you wrote 8i minus 15, it would be correct. Okay. So there's a question about the graph here. And if you haven't done graphing, I can't really review it here. We're not going to use it too well. We're going to use it on Thursday, so maybe I'll review it then. But 1 plus 4i, we go over 1 and up 4. And if we had minus 2 minus I, we go over 2 and down here. So this would be minus 2 minus, oops. I'm so in the habit of writing commas there. Minus 2 minus I would be this point. Okay. Okay, so those are the complex numbers, and okay, the question, how to get the minus 16, I times I, and I should have reviewed this up here. What this means, because we know that the square root of minus 1 times the square root of minus 1 has to be minus 1. So then what that means is I times I is minus 1. And that is, if we're working in complex numbers, that is really the only new thing we have to remember. Okay. So there's a question, how many complex numbers are there? We're actually going to see that later today. So I'll put that off. And the complex numbers and graphs, we're going to talk about that again on Thursday. And for now, it's enough to see what we have here. But I will review it again on Thursday for sure in more detail. Okay, so we talked about sets already, but now I want to go back and talk about what a set is. This is George Cantor. He developed set theory he was actually quite young. He was in his 20s, I think, when he developed set theory. So it was in the 19th century. And what he said was a set is a collection of definite, distinct objects. Okay. Now I'm going to tell you what these two words mean. And collection just means we have these brackets or braces. And we're going to say, you know, this is a collection. This is our way of saying it's a collection. Okay. Definite. And here's an example. This is the roster notation. And we just list them like a class roster. And what we say in symbols is A belongs to S. B belongs to S, and C belongs to S. Usually we give a set a name. Okay, now here, this is set builder notation. We've said X is a real number, and here it's a bold, not the way I've been doing it. X is bigger than 1. That's the set builder notation. Now, definite's an important thing here. Definite means we know what we're talking about. So if I say the set of all large numbers, that's not a set, because you might think 100 is large, and I might think, no, 100's not large, 1,000 is large. And then our friend might say, well, no, those aren't large numbers, 1,000,000 is large. So we have to know what's in the set. So here what we're doing is we're saying X is a real number and X is bigger than 100. So for sure, 200's in the set. 100.0001 is in the set. 100 is not in the set because it's not bigger than 100. 99 isn't in the set. So it has to be definite. And now the next one, oh, yeah. Okay, now I'm going to confuse you. Okay, now it's not really nice to confuse people, but I'm just going to have to do it. So, if we have a set, we have to know what's in the set. Okay, somebody's saying 90 is a big number. Okay, I don't know, 90. Okay, if you get 90 on a test, it's a big number. But if you're talking about pennies, 90 is not a big number. So that's why I put a big X here, the set of all large numbers. I'm never going to tell you something like that. And I don't want you to ever tell me something like that. You can tell me something like this. And so this is okay. But, mathematicians were precise. We can't say a large number. I can say 99, but I can't say a large number. Okay, like in this context. Okay, now there's this story. It's from ancient Greece and maybe a lot of other places. And there's a city. So here's a city. And there's a barber. How can we judge large numbers? We can't. But today I'm going to give you some really, really big numbers. And then maybe we can. So there's a barber and he shaves people. And he shaves everyone who doesn't shave themselves. So if somebody shaves themselves, they don't go to the barber. If they have a beard, they don't go to the barber. But, we're talking about the people that shave themselves. And the question is, who shaves the barber? Okay, somebody says he shaves himself. Okay. But he only shaves the people who don't shave themselves. If he shaves himself, then he's one of the people that doesn't shave himself. But if he doesn't shave himself, he shaves himself. And somebody's saying another barber, one barber, okay? His wife. It's confusing. Okay, whoever said it's confusing has the absolute best answer. Okay, there's only one barber and his wife, he won't let his wife near his beard, okay? So this is confusing. Oops, I hit the wrong button on my pen again. So it's confusing and my pen got confused. Okay, he's not going to shave himself, so he won't cut it. Well, then if he doesn't cut it, he's going to cut it. So this is what we call a paradox. And a paradox is something that doesn't make sense. And I'll give you another paradox. This is sort of like a story. But what if I say to you, this sentence, and if you know of any of these, you can let me know. What if I say to you, this sentence is false? Somebody says they like paradoxes. Mathematicians love them. Time traveling, yeah, time traveling is a paradox. See, physicists think, okay, there's no such thing as a paradox. They just do it out and out. Okay. The grandfather paradox. What's the grandfather paradox? Somebody has to tell me that one. Okay. This sentence is false. Now, I want you to tell me, is it true or is it false? Oh, here's the grandfather paradox. If you go to the past and kill your grandfather, that wouldn't be very nice. Then you won't be born. So how could you kill your grandfather? Because you haven't been born. Yeah, okay, that's a real paradox. Okay. Okay, if we travel and kill our grandfather, then we wouldn't have been born, so that we wouldn't have been able to go back and kill our grandfather. Yeah, okay, I can't. Okay, this one. If it's false, then what it says is true. If it's true, then what it says is true and it tells us it's false. Okay? So this also, this is a paradox and this is a paradox. So what do mathematicians do? Mathematicians say no paradoxes. Okay? Just like computer scientists say no infinite do loops. In any discipline, you have to limit yourself. And mathematicians have learned that you just can't do paradoxes, so we don't deal with them. Now, that's all very well if you're talking about sentences being false, but when Cantor came along, oops, it's supposed to be a question mark. When Cantor came along, you know how, maybe your friends aren't like this, but you know how you come up with an idea and you have a friend that always tells you what's wrong with it? Does anybody have a friend like that? Okay. So Bertrand Russell came up with this idea. He was a very, very famous mathematician, philosopher. And he said, think about this, the set of all sets that do not contain themselves. And you can write it like this. This is set builder notation. So you have the sets. A is not an element of itself. So this is the set, and Bertrand Russell said, see, I can be pretty clever. Is S an element of itself or not? Well, if it's not an element of itself, it satisfies this condition. But that means it's not an element of itself. But if it's not an element of itself, it satisfies the condition, so it has to be. So this is also a paradox. And if you don't understand this completely, it's a good sign. It means nobody can confuse you. So anyway, Bertrand Russell said, see, you thought sets were so beautiful, but now here's a mess, and what are you going to do about it? Well, Cantor actually passed on before they found a resolution, but mathematicians are still working out different ways to deal with this. And one way that they deal with it is they say, we only deal with these kinds of sets. And somebody says they don't understand paradoxes, it's fine. If you don't understand a paradox, I'm never going to give you another paradox again. And if somebody ever gives you something you can't understand, you don't want to deal with it. Anyway, so that means we have to know what's in the set. If I give you a set, you absolutely have to know what's in it and what's not in it. And if I give you a set like this, or a set of large numbers, something like this, you say to me, you haven't defined a set properly. Okay. Now, no elements distinct means no elements are repeated. And I came up with kind of a weird example here. I don't know if it's a very good one, but if I say, well, x squared is 1, or the absolute value of x is 1, you can say, well, here it could can we build a new paradox theory? I think there are people working on things like that, how to deal with paradoxes. Okay, so no repetitions. And the other thing about a set is the elements are not ordered. They're not in order. So the set ABC is the same as the set BCA. Okay, now what I want to do is I want to ask you some things. I want you to tell me, and I'm going to write a few sets out before I talk about the answers. So x is a real number, and x squared is 4. Now, I want you to think about these. Don't give me an answer yet. you can put these in the chat if you want. Okay. So he says the third one is a paradox. Okay, so what I'd like you to do is take a minute or two and figure out what these are. Oh, let me do another one because I'm so eager to make you work. Oops. Okay, now let's see if I can get all these on the screen at once. Okay, so there we go. I'm just going to write out what this means in words. The vertical line means such that. Okay, I'm seeing some answers here. Okay. Okay, so I've got x equals plus or minus 2. So what I would do here is I would write, somebody says x equals plus or minus 2, but because I have this as a set, I'm going to give the answer as a set, and I'm going to write the set like this. Okay. So because I set it as a set, I'm going to have it equal to a set. Okay, those are real numbers. Now the second one, well, you know, it really didn't matter whether I was talking about real numbers or integers. And so I get 2 and minus 2. Okay, the answers are exactly the same. And one thing that's very, very important in mathematics, and it's really easy to get sloppy about it, and that is if I have an equal sign and I have a set over here, I better have a set over here. Just like if I have, well, usually you have numbers, but I would never say the set of 1, 2, 3 equals 5 or 6 or something. I'm thinking of adding them up. I can't do anything like that because I've got a set and I've got a number. Okay. Now, what about this last one? I'm getting all kinds of interesting answers. Oh, okay, I finally got the answer that is what we're going to use. Are there any integers when we square them, we get -4? No, that's why we had to invent complex numbers. So here, one way we could do it is we could do like this. It's the set that doesn't have anything in it. It's the empty set. Now, for a minute, you might think, well, why would I have an empty set? And it's in a way kind of like thinking, why would I have the number 0? Well, as soon as you're doing subtraction, you might have 10 minus 10. And when you have 10 minus 10, you need 0. And here, I just did something innocently. I wasn't even thinking I was going to get the null set. I was just thinking I was going to fool you or challenge you. And then we got the empty set. It's also written like this. It's the Greek letter phi. And you will see this sometime. Or a 0 with a line through it. And so, this is used for other things. So if you're in the context of set theory, this is going to be the empty set. Okay. Now, down here, I see some answers in here. 2 minus 2, 3. That's correct. Because we could square it and get 4. We could cube it and get 27. So these are correct. Now this one, these two sets are not the same because here we have an integer, here we have a complex number. So now here we get 2i and minus 2i. And I'm seeing some correct answers in the chat. Okay, so those are some examples of sets. Oh, another thing is the elements are not ordered. So if you gave me 2i minus 2i, or you gave me minus 2i, 2i, same thing, they're not ordered. And in fact, and this is probably why sets are so important. Sets are about as simple as you can get. And in physics, they have the idea of the unified field of physics, the basis of physics. In mathematics, we have the idea of set theory. It's the basis of mathematics. Everything can be regarded as some kind of a set. The number systems, we review them in terms of sets. They're sets. And we'll see tomorrow that we can think of a set with some structure on it. But right now, we've got a set. The elements aren't ordered. They're definite. They're distinct. There's really only one thing we can say about a set. And that's how many elements are in it. And that's called the cardinality. And the cardinality, we use these vertical lines. These are the same lines we use up here, but here we had one of them and it meant such that. Here it's like the absolute value. Like, the absolute value of minus 2 is 2. The absolute value of 13 is 13, and so on. So here, the absolute value of a number says, well, don't pay any attention to the sign. But here, the absolute value of a set, it's called the cardinality, is just how many elements are in the set. Okay. And, here this is real easy. We can just go 1, 2, 3, 3 elements, cardinality 3. Now, let's see. I don't know what it's like today, but yesterday I saw some pictures on Zoom. 2 different pictures had the same name. And I think it was because two different people had logged in with the same account. I've done that myself. If I'm on Zoom, sometimes I'll log in and people say, why are the two Kathy Gorinis? Well, they're not. Anyway, how do we know there's the same number of things? One is to count. You know, if I have the set EFG or EGH, whatever, that's 3. They have the same number of elements. But what if they're a really, really big set? What if they're a really, really big set? How do I know if 2 sets are the same? Well, Cantor came up with this idea, and he used the analogy of a waltz, a ball. If all the ladies are dancing and there are some men off around the sides, there's more men than ladies. If all the men are dancing with ladies, each one has a partner, and there's ladies around, there's more ladies. Or if you go into a lecture hall and everyone is sitting in a seat and there's empty seats, you know there's more seats than people. If you go into a lecture hall and all the seats are full and there's people wandering around, you know there's more people than seats. So Cantor came up with the idea of a one-to-one correspondence. He said, if I can pair up the elements, even without counting, then I know they have the same number of elements. And, you know, that technique, you know, you don't need it for things that have 3 elements. But he said, and now I'm getting into what is so amazing about set theory. And that is the idea of an infinite set. In fact, Cantor came up with the idea of set theory because he was dealing with problems in calculus. They involved trigonometry. And there were infinite sets, there were infinite sets of points, and he didn't know how to deal with them. Well, they weren't sets of points. I take that back. There were infinitely many points, excuse me, and he didn't know how to deal with them. So he came up with the idea of a set. And he said, okay, if we have infinitely many points, we can put them into a set, and we can treat that set as a whole. So before we had all these numbers, now we have one set. And we can talk about different sets. Now, I want to go back. This is Cantor. This is 19th century. I want to go back to Galileo. And he was the guy that was in Pisa, Italy. There was a tower, and it's still leaning. And he said, gravity, it doesn't matter whether something's big or small, it's going to fall at the same rate. So he went up to the top of the tower and dropped 2 balls. One was big and one was small. And they landed at the same time. Okay. So he said, gravity is a force that treats things equally. And before that, people hadn't understood that. And so he's regarded, this is Galileo up here throwing his balls down. Before that, you know, people just thought about physics. And he is regarded as the father of experimental science because he said, I want to do an experiment. Okay. But he also said, okay, I've got brackets here, but he said, look at this. He thought it was a paradox, but Cantor came to the rescue. He said, look at this. And then look at this. One, two, three, 4, 5, 6, 7, 8, 9, 10, blah, 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 like that. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. It just goes on. And he said, look at these two. Everything in the bottom one you can find in the top one. But the top one has extras, 2 and 3, 4. Yeah, 5 is extra up here. So he said, you know, look at that. In the top, there's extras that we don't have in the bottom. But then, then he said, well, but you know what? Every number has a square. And he was confused by this. He said, we have a paradox here, is a problem. I don't want to deal with it. In fact, he said, let's not deal with the infinite. He said, it's all well and good to talk about throwing things off the Tower of Pisa. It's all well and good about looking through telescopes and seeing planets, but we don't want to talk about infinity. And Cantor came along and said, no, you know, we want to deal with infinity. We have to deal with infinity. Infinity is important in mathematics. We have to be able to deal with it. And he said, remember when I said how to convert a repeating decimal to a fraction? I said, we need a technique. This is what Cantor said. We need a technique, and our technique is going to be one-to-one correspondence. And he said, look, oops. He said, look, I can make a one-to-one correspondence. I'm going to say these two sets have the same cardinality. He said they don't have the same elements. They're different sets, but there's something the same about them. We can put them in one-to-one correspondence. And of course, 36, I have to remember that's going to be 6, 7, 8. And over here, we're going to have 49, like that. He said, I can put them in one-to-one correspondence. And so I'm going to say they have the same cardinality. I'm not going to say they're the same set because they have different elements. And so Galileo was right about that. They had different number of elements. But, I mean, they have different elements. They have different particular elements, but they have the same cardinality. And he used the same cardinality because he didn't want people to freak out. How can you count to infinity? Because you know you can't count to infinity, but you can talk about one-to-one correspondence. And then he had a lot of fun, of course, because he could say, well, the even numbers have the same cardinality. Let's see. Even numbers, because I'm going to do this with this, this with this, this with this, this with this, and like that. So lots of sets have the same cardinality. And Cantor said, you know, just like if we have this set, we say the cardinality is 3. He used the first letter of the Hebrew alphabet, alpha, and put a 0 down here, alpha sub 0 or alpha naught. Excuse me, aleph. not alpha, aleph naught, or aleph 0. He used that because he wanted a symbol that wasn't being used already. And especially at that time, the printers had they had the Hebrew alphabet because they would print the Bible. So he used aleph. And of course, now with computers, you can use any symbol you want, and that's a lot more fun. Now, let's see. What do I have here? Oh, that was this one. Uppers. Okay. Okay, so let's go back here. Let's go. Let's go. Okay, let's talk about Hilbert's Hotel. Okay, Hilbert's Hotel. So anyway, this was really, really nice, and this helped people understand infinite sets very, very well. But of course, it's still complicated. Okay. Okay. Yeah. These three sets all have the same cardinality here. These three have the same cardinality. And connection between Greek and Hebrew. I think this is actually the only letter from the Hebrew alphabet that mathematicians use, but they use lots of Greek letters like pi and rho and gamma, and physicists use them too. Is there a difference between infinite and imaginary? There sure is. Sure is. This is infinite. When we say okay, now imaginary, in English, the word imaginary means you just dream it up. In mathematics, imaginary means the square root of -1. And if you're talking to your friends about infinity, they can think, oh, you just dreamed that up. So words, mathematics has ideas that come up that don't have, they have to invent words. Like computer science, they have to invent words all the time, like a bit. A bit in computer science was a word that people invented because it was a binary digit, and they made bit out of it. So like that, in mathematics, we invent words all the time. But Hilbert said, you know, Cantor, this is such a beautiful idea. And we'll see later what he said about Cantor's beautiful idea. He said, but I want people to have a better understanding of the idea. So let's imagine a hotel, and in the picture, you don't see the end of the hotel because it goes on infinitely. So Hilbert's Hotel has rooms, infinitely many rooms, 1, 2, 3, 4, like that. And that's why we don't see the end. So this is room 1, room 2, room 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, on and on and on. Okay, so that's Hilbert's Hotel. And right now it's full because this guy is in this room, this is in this room. Everybody's got a room, the hotel is full. Then a new customer comes along and he says, I need a room. It's 12 o'clock at night and there's no other hotel in the neighborhood, and I need a room. And the manager, you know, a manager of a hotel hates to turn somebody away. So the manager of the hotel says, Where's the manager is here. This is the manager. The manager of the hotel says, no problem. What he does is he says, okay, you're in room 1, move to room 2. He tells the guy in room 2 to move into room 3. He tells the guy in room 3 to move into room 4. And okay, I mean, this is an example. Well, it's not even an example. It's an imaginary. It's a dream example, because you can't do this to people. You can't move every single person in your hotel and expect return business. But Hilbert's hotel, we can. And so everybody, and we have freed up one room, and the new person lands in room 1, and everybody has a room. Okay. So this is Hilbert's hotel. Now I've got to get my I've got to get you something else here. So let me just do that in 1 second. This is in your handout, which you have online. I think you should have gotten it. Okay, so this. Oh. Okay. Okay, so this, you should have it. You can open it up on another screen, but I should have put this in already. Let's see. Oops, too big. Okay, I think that's good size. It's a good size for me anyway. So again, you have this on your sheet. Now what am I going to do? Okay. Okay, so this is a little description of Hilbert's hotel. Okay, so you're students of the infinite. You understand infinity right now, and you need to help the manager. And the rules are that anybody that comes in, you have to keep the hotel, you have to give them a room. Otherwise, you're going to lose business. But you also want to keep the hotel full. And these are really marvelous guests. They don't mind moving around. And okay, so here, these are the problems that I want you to do. And let's see, this is not supposed to be here. Okay, and okay, it's going to get complicated. So we're going to have to go back and forth. But this first question is, the hotel is completely full, and oh my God, I am getting questions. People are wondering about the poor guy in the last room. Oops. Oh my gosh, what happened here? Oh, I know. I can move this. Let's see if I can get this in the right place. People are worried about the last guy. Oh dear. Okay, I know what to do. Yeah, because, you know, we really do have to worry about that last guy. He's an important customer. Okay. One, two, three, 4, 5, 6, 7. Okay, now we were talking about big numbers before. So the guy in room 99, he thinks he has a big number, right? He says, I've got a big number. What about the guy in room 1,000,000,000,000? Okay, this guy says, well, I have a really big number. My number is bigger than your number. Is there a guy in the last room? Okay, we're not going to kick anybody out of the hotel. We'll lose money. We'll lose our reputation. No way we're going to kick anybody out. And we're not going to make 2 customers share a room. That is just, we lose business that way as well. Okay, now Hilbert's hotel is not a real hotel. It has infinitely many rooms. Okay. Even if it's full, everybody has a room. Everybody can move to the next room. If you're in room N, you can move into the room N+1. Oops, not N plus N. N+1. If you're in the room 100, you can move into 101. And then you say, well, what about the guy in 101? Well, that guy got sent to 102. Is there anybody who can go to a room that's not empty because that guy got moved? No. Everybody got moved. There's no last room. There's no last room at all. That's what infinity means. That's what ... means. Do you remember, I know, well, for me it was longer than you, but do you remember when you first learned how to count? Not just 1, 2, 3, but you learned like 20 and 100 and 1,000 and like that. And do you remember at one point you realized you could count forever? Anybody? Anybody remember that? Does anybody have a little sibling who learned how to count and kept counting? If you run across a kid, oh yeah, we've got some, yes, you've got a kid, maybe they're in 1st grade, 2nd grade, and they, oh, my younger brother, okay, so somebody's younger brother, and they learn how to count, and then they won't stop. That's all they want to do, and they're never going to finish. That's the whole thing about infinity. And infinity is mind-boggling. Grade 2. Okay, somebody remembers like yesterday. Is one of the most exciting experiences because you go, it can go on forever, forever and ever and ever. Now, the thing is, you think that that's, you think that's beyond you. But here's the thing that Hilbert said. It's not beyond you. You can imagine the whole totality of infinitely many numbers. It just shows how incredibly infinite your consciousness is. Your consciousness can imagine, can hold in its awareness infinity. Poets say this. For next time, I'll try to get you a poem. There's some poems where they talk about infinity. But poets like it. Mathematicians like it. Little kids like it. You can comprehend infinity. You can't do it step by step, but you can do it as a whole. Okay, it's just beautiful. So let's see where we go here. Hilbert's Hotel. I shouldn't say first invented. That's what invent means. Okay, you have one more guess. Now, okay, this is I answered this one for you. You don't want to throw anybody out. Okay, now we've got the hotel. It's full. And the guests in room 5 and 12 leave. It's not full anymore. And the manager comes and says, look, here I have this hotel. I've got infinitely many rooms. We can make lots and lots of money. But you've got empty rooms. What rooms? You've got 5 and 12 are empty. Okay. And you're at the front desk and the manager is having a fit because he's got 2 empty rooms. What can you do? You don't want to do what you did before. You don't want to put person in 1 into room 2 because then you'll have another empty room. But what can you do to fill up the rooms? Okay, somebody's offering their room. No, you're not going to give up your room. Okay. Okay, we got some answers here. Okay. Yeah, customers can shift in either direction. Okay, so somebody is saying shift back. So 6 is going to shift back. 7's going to shift. 8's going to shift. 9's going to shift. 10's going to shift. 1, 2, 3, 4, they stay where they are. 11's going to go into room that. Well, there's no 13 is going to go into room 11. Yeah, 6 to 5. 12 can't go to 11. There's nobody in 12. 13 goes to that. And then after that, you can have a formula. So after 13, if you're in room X, goes to X minus 2. Okay. Okay. No, somebody says you go to 5 and the manager goes to 12. No, we're not going to let you move into your own hotel. You're going to lose revenue that way, giving out free rooms. Okay. So those are the rules. Okay. Build a new hotel. Okay. Now we may need to build a new hotel and we'll see that in a minute. Okay, now we have cosmonauts coming. The hotel is full. And the cosmonauts, there's infinitely many cosmonauts. They come from another galaxy where there's infinitely many people. Okay, so you have rooms. You have rooms 1, 2, 3, 4, 5. Okay. You have these rooms and the cosmonauts come in. Now, conveniently, they're numbered. So these are the rooms. And they're full. And you have cosmonauts. And they've been flying around the universe, and they come to your hotel, and they want, okay, somebody says build a new one. Well, we're not going to build a new one because that's going to take too much time to build an infinite hotel. So we have these infinitely many cosmonauts, and they have good money. And the manager says, put them up. We're not going to turn them away. Okay, so what I'm getting an answer here, but what I would like you to do is think about this. I've got one answer, but I'm going to let everybody think about it. Okay. Now, another thing that you can do, in the chat, I have a formula. But if you want to draw a picture, the way I did with the previous example, you can draw a picture and hold it up to the camera. And there's a lot of hosts, and I can only see a few of the pictures, but one of the hosts can pin it if you hold up a picture. So we'll do that. Make a new room. Okay, you guys are too creative. The manager says we're not going to make new rooms. We're not going to renumber the rooms. We're not going to build a new hotel. You're stuck with what we have. So you have to deal with it in a different way, in a kind of creative way. Divide the rooms. Okay, the cosmonauts. Have you ever seen a cosmonaut? Actually, I haven't, but we're not going to divide the rooms in half because a cosmonaut has this huge spacesuit. He's going to have to put it in the closet. The other guest is not going to be happy. Okay, 2 guys are going to share a room. Okay, no. Would you share a room with a cosmonaut? I wouldn't. Okay, rename the rooms. No, we're not going to rename the rooms. You guys are too creative. Yeah, this is being recorded. You don't have to worry. What are we going to do with the cosmonauts? And they won't all go into one room either. They don't like each other any better than the guests do. Okay, somebody is saying infinity plus infinity is infinity. Yeah, we're going to see that. Okay, somebody says just put them in there. There's infinitely many rooms. But that's not good enough. And the reason I say it's not good enough is because the cosmonaut is going to say, well, I need a key. Which room do I get? And the people that are already there, they're saying, look, I was here already. I need a room. Okay, somebody is saying we can shift the whole set of guests until we get enough space. That is exactly what we want to do. But the question I have is just let them walk. Okay. Okay. Okay, Hilbert, somebody said just put them in different rooms. Put them in the room called infinity. Hilbert would say, excuse me, well, Hilbert too would say, but Cantor would say, that's not definite. Pop everyone in from the start, then the wall. Oh, okay, now we're good. Okay, 1 to 2 to 3. Okay, if we go 1 to 2 to 3, we're only going to get finitely many rooms. And we don't have a room called infinity. Okay, funnily enough, the first person that put an answer in, these are direct messages, so I guess you guys aren't seeing them. The first person put them in, did the right thing, but I want to see some more. Oh, here's another one. Okay. Madhava, let's see what you did. Let's look at this. X goes to 2X, new customers. Okay, so let's do this. Very good. So 1 goes to 2. 2 goes to 4. Oops, no, I don't want to do it that way. 2 goes to 4. 3 goes to 6. 4 goes to 8. 5 goes to 10. And then what we have with the cosmonauts. So now the people you have, the current guests, this is definite. They each know exactly where they're going, and they leave empty rooms. And not only do they leave empty rooms, they leave infinitely many rooms empty. So this guy goes here to 1 because 1 got emptied out. 3 got emptied out. 4 got filled up, so we go to 5. 6 got filled up, we go to 7. And so here's the formula. The person in room X goes to 2X. And then the cosmonauts, because each cosmonaut had a number, and the cosmonaut number X goes into room 2X minus 1. Okay. And so 3 goes to 2 times 3 minus 1 is 5. 2 times 4 minus 1 is 7. So we've done it. Okay, so we did it. We didn't have to build a new hotel. We didn't have to renumber the rooms. We didn't have to double up. And of course, this is it's what they call in physics a thought experiment. Okay. Uh-oh. Now what do we do? The hotel is full. The astronauts leave. There's infinitely many astronauts. At least we know where they were. They were in the odd-numbered rooms. And so the manager says, what is going on? The hotel was completely full yesterday. Today, half the rooms are empty. What kind of marketing is that? Just ridiculous. You better fill up the hotel. So let me see if I can draw any kind of a picture. These are the rooms. and the odd numbered rooms are empty. Okay, so we've got guests only in the even numbered rooms. We've got infinitely many rooms empty. And you know, you're the manager. No, you're the front desk. Where are we going to go? Where are we going to go? Okay. So we've got some ideas here. We've got two ideas. One idea, and I'm going to write it as a formula because that's how you're giving it to me. One idea is the person in room X goes to the previous room, and another idea is that it goes to half the room. So there's two rules that are being proposed, and we want to see, they both look good, don't they? So we want to test them. And this is what mathematicians do all the time. Mathematics teachers don't usually do it because they like to act like they're smart. But when you're solving a problem, the best thing to do is come up with some ideas and then test. Are these ideas going to work for you? So let's test this first one. And, you know, if you test it and it's wrong, well, you know, that's too bad. But in the process of testing it, you may understand something else about the problem. So if this goes to the previous one, so let's see. So 2 is going to go to 1. So 1 would be full. 4 would go to 3. So 3 would be full. 6 would go to 5. So 5 would be full. But that's still, then that what's happened is now we've got the even numbers empty. Okay? Do you see how that works? And yeah, now the even ones are empty. So that's why it's so important to come up with an idea and then test it. So this doesn't work. Okay. Because everybody moves over one, different rooms are empty, but rooms are empty. Now let's see if I can get rid of these. Okay, but when you come up with an idea, and it was a good idea, test it. Because if you can test it, then you can determine if it's correct. So now let's look at this formula. X goes to a half. So 2 goes to 1. 4 goes to 2. 6 goes to 3. 8 goes to 4. So we filled up 1 and 2 and 3 and 4. So we're doing well. And now this has to be an imaginary hotel because you don't want to tell the person in room 1000 that they have to go to room 500. They say, well, you know, how am I going to do that? You know, I can't do that. It's too far. So, but it doesn't matter because this is an imaginary hotel and everybody is in an even room and they know exactly where they go. And if the manager says, well, did you fill up room 101? The manager, then you tell the manager, yeah, the guy in 202 went to 101. Did you fill up room 99? Yeah, because the guy in 198 went over there. So you know who filled up every room. So this works. Okay, here's another one. Okay, the Galaxy Club games, cup games, 2 tour groups, each have infinitely many members. They both booked with the hotel and the hotel's empty when they arrive. So here are the rooms, 1, 2, 3, 4, 5, 6, 7. And there's tour group A. They're the green team. And the red team. And they come all at once. Where are you going to put them? And you can't put all the A's in first and then the B's in because you'll have a riot on your hands. They've traveled a long distance, and where are you going to put them? And if anybody used to be a school teacher, school teachers know how to do this. Okay. Yep, I'm getting good answers here. Odds and evens. So we put A1, let's do B. So B1, B2, B3, B4, and then A1, A2, like that. Beautiful. So you interleave them that way. Okay, now there's some more examples here, but I want to get back to some of the other topics of the day. Cardinality. Oh my gosh, this is, Cantor gave a proof. And when he did the proof, he said, I can see the proof, but I don't believe it. So I'm going to show you this. We have the unit square and the unit interval. So the unit interval, when we have square brackets like this, we mean we include the endpoint. So this is the unit interval. This goes from 0 to 1. And here is the Cartesian product of the unit interval. So it's like R cross R, but it's just this. So every number here is like X. Well, yeah, we'll just say X. And every number here is like X, Y. Okay. Now, tell me, do you think you can get a one-to-one correspondence between those two sets? Do you think you can get a one-to-one correspondence? Hilbert said, Cantor said, you know, look, they're completely different. One's a line and one's a square, you know, filled in line, filled in square. But Cantor said, well, let's try. And so he said, look at something here. It looks like point A, B, C, D, E, F. Okay. The numbers between 0 and 1, decimal numbers, over here, we're going to have pairs, and I'm going to use Greek letters here. I'm running out of letters. Let's use, Okay, I'm going to use XYZ, even though I can't keep going, but you know what I mean. I have one number up here. How do I get a one-to-one correspondence? Well, Cantor had a beautiful idea. He said, take a number up here, and it's like peel it apart. And so he said, take this and write point A, C, E, point B, D, F. So he has said, see, if I have a number up here, I can get one down here. And if I have a number down here, it's like shuffling. You know, you have cards and you take them and you go, you put them into one deck. He said something down here, I'm going to use red for this. Something down here, I can just merge. I can put the two together. And I'm going to have point alpha X, beta Y, gamma Z, delta W, ... And he said, look, you can do it like this. I see it, but it's almost unbelievable. Okay. Now, the thing is, he's got a one-to-one correspondence. It doesn't have anything to do with distance. You know, 2 points that are really close down here could end up really far apart up here. That's not the point, because sets don't have structure. He's not thinking about the structure that the sets have. Okay. So that's this one. Now this one is really important. He said the integers have cardinality aleph naught, and the integers, well, these are the natural numbers. So I'm doing 0, 1, 2, 3, 4, 5, 6. Now the rational numbers. How can we understand the rational numbers? Cantor said these are going to have the same cardinality. But if you think about it, there's way more rational numbers. Way more rational numbers than natural numbers. But we saw that with Galileo, just because there's like we can find more things there, doesn't mean we can't find a pattern. So Cantor, this is one of the things, one of the principles about knowledge is knowledge has organizing power. This is a principle of information theory. Knowledge has organizing power. So we know all about the rational numbers. And what Cantor said was like, just do this. Oops. Okay, here are some rational numbers. Now, this isn't good enough. These are all the rationals that have 1 on top in the numerator. So you got to put dot, dot, dot. Well, then there's a whole lot of numbers that have 2 in the numerator. Okay. Now, okay, I know what you're thinking. You're thinking, well, we had 2 over, oh, let me use a different color. We had 2 over 2 is the same as 1. 2 over 4 is the same as a half. This is the same as a third, a fourth, a fifth. Okay, so we can forget about those, but at least we know we have everything with 2 in a numerator. We can do the same for 3. And of course, we're going to get some repeats. Okay. But Cantor said, that's not a problem. I don't mind repeats. But what I am sure of is I have all the rationals here. Every single rational is there. And if you say, well, I don't see 17 over 25. Okay. I don't see 17 over 25. Well, if you go down to the 17th row and over to the 25th spot, you'll find 17 over 25. Okay. So what Cantor said is, well, we know the natural numbers, 0, 1, 2, 3, 4. We can make sense out of those. We can list them in order. And he even called these countable. We can just go in order, no problem. The rational numbers, we can't make a list out of them easily. The reason we can't is because if we do the numerators 1, we don't have the numerators 2. If we do all the numerators 2, so we have to do a grid. He said use a grid, use an array, put them this way. And then what he said was, now go through the array. We can't go through the array like go the first row and then the second row, because we'll never get through the first row. Okay, it goes infinitely in that direction. We can't go down the first column because we'll never get to the second column. So he said, do it this way. Yeah, do it this way. like this. Do you see how eventually you're going to get everywhere? Eventually you're going to get to 17 over 25. Now, this isn't the only way you could do it. You could have gone down first and then over next, or you could have gone zigzag or something. You can find other ways of doing it. But Cantor said these have the same cardinality. And the way he did it, he showed a one-to-one correspondence. Cantor showed a one-to-one correspondence. Okay. Does anybody understand this? Have I lost people? Can you raise your hand if you okay. Some people are oh, good. Okay. Not infinitely many people, but we got a lot of people. Okay. This is great. So some of you are understanding it. And let's see how high we can go. 70. Okay, good. So if you didn't understand it, we may have time to review it tomorrow, or you can ask your friend that understood it. Okay. Now we're going to do something really, really cool. So we have the counting numbers. Well, actually, let's not use 0. It doesn't matter. We already saw with Hilbert's Hotel, if I put a 0 in or not, same cardinality. Okay, so this is Aleph Naught. And Cantor said, what about the real numbers? And he didn't even say, what about the real numbers? He said, let's look at the open interval from 0 to 1. Oops, 0 to 1. And a number here, one example would be 0.5. Another example would be 0.32, 312. Well, let's do 312, 312. Another example would be 0.756. Lots and lots of numbers in there. Now, I don't think, well, it's just like the fractions. I can't list them all. Cantor came up with a way to list the rationals. Oh dear. And he said, I can't do it. I just can't do it. I can't find a way. Now, I'm going to tell you something about mathematics in general. Sometimes you can prove something exists. Okay. Like I asked you, does the square root of 4 exist? And you say yes, because 2 times 2 is 4. Okay. So you have proved that the square root of 4 exists. Now, the Greeks had a problem with the square root of 2. It's really hard. Now, it does exist, but there's no rational here. There's no rational number. If you want to prove something doesn't exist, it's hard. So, for example, your friend says dragons exist. There are dragons in our city. You say to them, well, I don't think you're right. I've never seen a dragon. and they say, well, prove to me there's no dragons. It's really hard to prove something doesn't exist because you have to show there isn't one. And you say to your friend, well, you know, I've never seen a dragon. And your friend says, well, there's one behind my house. And you go, okay, well, can I come see it? And your friend says, well, sure. And you get there and there's no dragon. And your friend says, well, he moved. He was here yesterday, but now he's in another place. Okay. So to prove something exists, you just show it. And you have the problem, you want to prove it doesn't exist. It's hard because your friend keeps saying, well, he's over there today. No, he's over there today. So this is what Cantor did. Cantor said, he went out on a limb. He said there is no one-to-one correspondence between the real numbers and the counting numbers. It's a 3. That is hard to do, to show something doesn't exist. So he used a technique. It's called the technique of contradiction, proof by contradiction. And you may have seen this somewhere in your work before in mathematics. But what he did was he said, suppose there is one. Okay. And, you know, suppose there is one. So we have 1, 2, 3, 4, 5. And he said, you know, I don't really care what those numbers are. Maybe they're 0.5, 0.312, maybe they're 0.756. Maybe they're 0.20. I'm going to put zeros forever. You'll see why in a minute. He says, somebody gave me this list. I don't know who made it up. One of you guys made it up, probably. Okay, so, maybe it's 1, 3, 4, 2, like that. So we have this list. Okay, so Cantor is being like the naysayer, the person that says no. So you come with a list. You say, okay, I think there is a one-to-one correspondence, and I have a list. And Cantor says, you think you're so smart, but I'm going to find something that's not on your list. I'm going to look at these numbers. And if I were neater, these would have been in a diagonal. Well, they're kind of in a diagonal. He said, look at your first decimal for your first number, second decimal for the second, third decimal for the third, fourth decimal for the fourth, like that. So it's called Cantor's diagonal proof because he went down here in a diagonal. And he said, I'm going to come up with a number. And I'm going to say, put my decimal place, and I'm going to say, I want something different from 5. Well, 4 is different from 5. I want something different from 1. Well, 9 is different from 1. I want something different from 6. Well, 5 is different. Oops, this is the fourth one in the fourth. See, I want the fourth one in the fourth. I want the fourth digit in the fourth row. 0, 1 is different. 1, 2, 3, 4, 5 is 1. So something different from 1. Well, 2 is different. And Cantor, he didn't give a number. Okay. because we've talked about infinity. With infinity, you can't give a number. You can't write it out to the end. But what you can do is you can give a procedure, and that's what Cantor did. And the beautiful thing about his procedure is it works for any list that anybody comes up with. If somebody comes up with a different list, I'll find a different number that's not on their list. Whatever, and so this is what Cantor said, whatever one-to-one correspondence you think you have, I can show that you don't have something on that list. Okay, now I'm going to stop here. I mean, not immediately, I've got to say a few things, but I'm not going to do anything new here. Maybe you could raise your hand if you understand this. Let's see if anybody is willing to say they understand it. What I'd like you to do is think about it, and we'll talk about it again tomorrow. Okay, so some people are raising their hands. But what Cantor proved is actually mind-boggling. What Cantor said was, you can have your counting numbers. And they're infinite. There's infinitely many. Infinitely many counting numbers. But then you can have the real numbers. I said I was going to talk about 0.999, but I'll do that tomorrow. And then you have the real numbers. And there's more. This is what Cantor showed. There's more of these. Okay. Somebody's saying there's a hidden meaning. My mind is going deep, but I can't find a pattern. Okay, here's the thing. This is a new idea for Cantor anyway. I remember distinctly the first time I understood this. I just was blown away, because my idea was, well, there's infinity. The universe must be infinite, because if you get to the edge, well, maybe you could keep going. I just said, okay, there's infinity, and that's that. What Cantor said was there are different sizes of infinity. He said the counting numbers, that's all if naught. That's countable. And he said there's the real numbers, and there's more of them. And how many more? Okay, now this is the thing, and this, I'm going to end on this, but it'll give you a lot to think about. He doesn't know how many more. Nobody knows how many more. There are some questions mathematicians have not figured out the answer to. So we don't know the answer to this. And so, anyway, let's see. Oh, this is the last thing I'm going to say. David Hilbert found this wonderful. And people were saying, well, set theory, who knows? How can you deal with the infinite? David Hilbert said, basically, Cantor created a paradise for us. No one shall expel us. And by that, he meant nobody is going to tell us that there's paradoxes we can't resolve, that there's problems we can't solve. He said set theory is a paradise. Infinity is a paradise. The consciousness, our minds, it's a great paradise. It's a tool that we can use to accomplish virtually anything. So this is where we'll end today. Tomorrow we'll review this, and I hope you have a chance to think about it, talk to your friends about it, and we'll talk about it again tomorrow. Okay? Thank you so much. Bye-bye.